So we're working in the OpenStax Statistics book, Chapter 9, so we're on the second tab of the Excel spreadsheet. So this is going to be working on a hypothesis testing example with swimming times. So just as a friendly reminder, you can always access the OpenStax text for free. You can look in the description of the video, and then the Excel workbook that I have, that is totally free. Go to divideandconquermath.com, go to the OpenStax Statistics section, and you can download it there. All right, so we have Jeffrey has an established mean time of 16.43 seconds for swimming the 25-yard freestyle with a standard deviation of 0.8 seconds. His dad thought that with some goggles he might swim faster, and so he timed Jeffrey for 15 25-yard freestyle swims, and his mean time with the goggles was 16 seconds. So Frank thought the goggles helped Jeffrey to swim faster, so we're going to conduct a hypothesis test using alpha equals 0.05. Okay, so we want to know in this case if Jeffrey has broken his average time. Now, a couple of things just to point out with this. This is always an important thing to note. So the way that this is worded, we have an established mean time and an established standard deviation. This standard deviation, because it is established, that is what's making us believe that this is the normal distribution. So you always want to figure out, are you working with the normal distribution or student's t? And since it says established, that's like the assumption that we can make. Now, I don't have this in the spreadsheet that you have, but if you look at the slides or if you look in the book, so it's just important to note what are your hypotheses, because this is everything that you're testing against. So I talked about this in the previous tab, so you can always go back and watch that explanation, but just kind of some highlights here. So we want to figure out if he's actually swimming faster than this. And so since this is what we're testing against, this is what we're going to call the mean. So there's very often like two different means that you're talking about, and you have to keep them straight. So the one that you're testing against, that's kind of your established mean. So in this case, you can think of this mean as your established mean. And then that new mean that you're like using to as kind of your data to test with, that's going to be what we call our x. Okay. So that's the way that I label those things. So I've got this 16.43, sorry, 16.43. This is my established mean, x equals 16. That's kind of my new mean. My standard deviation, which I know in the back of my head is sigma, this is 0.8. And then the n that we're talking about is 15. Okay, now for this example, we're going to do this two different ways, because with hypothesis testing, you can use either p-values or critical values, and it is kind of up to you as to which one makes more sense. And I know sometimes when you first learn these things, it's like, oh, this is so annoying. I don't want to have to learn like more methods, but it's actually very helpful with hypothesis testing, because sometimes one of these ways can confuse you. And so it's nice to have like a second way to check yourself. You know what I mean? Okay, so first, let's talk about p-values. So this is very similar to the previous tab where we were talking about working with the bread. So once you come up with your data, then you need to like just translate it to your distribution of sample means. So the mean is the same. Your standard deviation, you're going to take, your standard deviation, there we go, standard deviation. So you're going to take your standard deviation divided by the square root of n. So I probably should have linked that n, sorry. And then for my test statistic, so we talked about this in the previous tab, but I'll just mention this again. So the test statistic is like, you don't technically need it when you're working with the normal distribution, but it's important to kind of understand the logic here, because it's going to matter when we actually move to the next tab. So you kind of want to understand like, what does all of this mean and where does this all fit together? Okay. So one way that you can compute your kind of area or your test statistic, or you can do your p-value computation, I guess is what I'm trying to say, is that, okay, I can use the normal distribution. So this is what the book does. So your established mean is the center of your normal distribution. And so then that other mean, so I say this is x, it's really technically an x bar, so you can see it's properly labeled here. But so here's kind of that new mean that we found, that 16. And so notice then I'm really trying to get the area from here to the tail. And that aligns with the direction of my alternative hypothesis, right? So I should be going boop, boop this way. So those two things should be aligned. Okay, so I'm trying to find this little sliver of area. And so from this, I can compute my normal distribution. So I'm computing to the left. So notice how my normal distribution is set up here. So I plug in 16. So notice I'm using the mean, I'm using the standard deviation that we calculated here, and then true. And so I get that this is 0.0186, so on and so forth. So this is one way I can calculate a p-value. The other way, and I talked about this in the previous tab, so the other way that you can calculate a p-value is by using the test statistic. So this is very important that you understand two ways to do this. Now, when you want to do this according to the test statistic, so instead of doing this p of x is less than 16, we're kind of thinking this is more being less than the test statistic. And in this case, when I'm making this computation, I'm using my test statistic. This is no longer the normal distribution. We're using the standard normal distribution. And so instead of having this mean here of 16.43, you would assume that now your mean would be for the standard normal distribution 0. And then your test statistic, so this negative 2.08. So instead of having 16 here, you would have negative 2.08, okay? All right, so that is our setup. And so I can then look at the formula here. So notice that when I do my computation in this case, I'm just using my test statistic. And so I get the same answer with either. And in both cases, so we say if p is low, the null must go, so we can reject our null hypothesis. So this is two different ways to calculate your p-value, just the logic kind of behind everything. And now we're going to compare critical values. So critical values are kind of a similar approach. It's just a slightly different way of kind of how we think about things. So we do the same thing. We need to know kind of some stuff about our distribution of sample means. So mean is the same, standard deviation is calculated the same. But what is critical with critical values, is you have to have a test statistic. So when we're talking p-values with the normal distribution, sometimes you can get away from having to use the test statistic, right? So this method here, when we just use the normal distribution, I didn't technically need the test statistic. But critical values require a test statistic. So that is something that I have to do, and I get the same test statistic that I had before. It's the same and it's the same. And then the other thing that you have to do is you have to figure out your critical value. And your critical value is always tied to whatever your alpha is. So we are talking about a left-tailed test, and so I need to figure out what is that bottom 5%, what is that z-score for the bottom 5%. So notice that the function I use here is I use norm.s.inverse 0.05. So that's the amount of area that we're looking at, right? So looking at this, I have my critical value and my test statistic. We are clearly in the standard normal distribution. So the way that this looks, I really like critical values actually, because I think it has a very nice visual. So you have your critical value, that negative 1.645. Here's your critical value. And then you put in your test statistic. So here's where my test statistic falls in relative to my critical value. So basically now what this has created is if your test statistic falls somewhere over here, kind of where the tail that we're testing in is, that's your reject zone. So I can really clearly see my test statistic falls in the reject zone. And so I can also say in this case that, yeah, I'm going to reject the null hypothesis. So there's two different ways that you can go about this. You can have a p-value where if your p-value is under your alpha value, so less than 0.05, then you reject. Or you do a critical value, and if you can see that your critical value is, in this case, less than your, falls in that kind of reject zone compared to your critical value, it's also a reject. So it's the same and it's the same. And they really are the same technique. It's just a different way to think about it. So in this case, you're computing an area, and then you're comparing that to that 0.05 area that you know that you want. So you're just comparing these two areas. Versus you're still using the 0.05 in the critical value, right? You're just coming up with a associated z-score along this axis, and then you're comparing your test statistic to that z-score. So it's either comparing two areas, comparing this area to the 0.05 area, or it's comparing z-scores. Your choice.